Hey all. I do have a slide link up here. So basically there is going to be a decent amount of code that's going to be throughout this presentation rather than having to either try to write it down or remember it or like try to take pictures in the middle of the presentation. Entire slide deck is already right here just to hopefully make life easy. If you decide later that you actually like the presentation and you want the slides then, I will also have it at the end as well. So I'll kind of give folks a second to grab that. All right, I'll just kind of repeat that then. So all of the slides are here on this bit.ly link. So because there is a lot of code that's going to be in this presentation, rather than having to try to write it down or remember it or anything like that, you can just grab the link now. If you decide at the end of the presentation that you decide, hey, this is actually an OK talk and I do want that code, then you can find the bit.ly link at the end as well. So don't worry about it too terribly much. It will be available just to make life hopefully a little bit easier with all of this. Oh, did everyone get that? Yeah? Or is it at the end? It's cool. So my name is Ruiz, and I am an engineer with the developer relations team on Google ML. So while my team actually covers a variety of topics, my main focus is on mobile and IoT devices. So today I want to introduce you to the Flutter plugin for TensorFlow Lite, which is entirely open source, and it's out there on GitHub. I'm also the main curator for this repo and whatnot for issues and PRs. So if anyone does want to contribute, please let me know. This is very much a community-driven project, so the more people that are setting up PRs and examples and documentation, all that fun stuff, just the better it is for everyone involved. So really, I think my goal here today is just to make sure that you can walk away with a vocabulary around machine learning, know how to apply those concepts with TensorFlow and Flutter, and then really have an idea around how Firebase can be used to complement both of those. So before we start, let's actually go ahead and cover just a few really high-level machine learning concepts. So while a traditional program is going to take a known input and a known function, or essentially a set of rules, to produce an output, machine learning actually takes a set of known inputs and known outputs. Then it tries to figure out what the function is between the two so that new outputs can be generated based on new inputs. So this process is called training, and it's kind of one of the main things people think of when they are thinking about machine learning. Honestly, though, it is a bit outside of the scope for this talk because the majority of the time we as mobile or web or just edge in general developers are going to be given the model by somebody else who has spent the time optimizing it and making sure that the model is really correct for what the problem is. So that said, if you are interested in training your own models, come find me. I will be at the event both days. I can kind of go over some things with like Model Maker or Vertex AI so that you can take your own data and train your own models for what you would use on these devices. So the next thing to know is that machine learning models do not really give you kind of correct answers, but what they do is they make predictions. So what models do is essentially they're going to take what they've learned during the training phase and then try to take a best guess at what they think that kind of correct-ish answer is based off of the new inputs. So really the biggest suggestion I have here is to not really rely 100% on what the model says, but use it as more of a tool to help guide decisions. Now, if you're perfectly confident and comfortable with 70% accuracy being good enough to make a decision in your app, perfect. It's all really going to depend on what you need for your own situation, and every app is going to be different. And then finally, machine learning is going to allow you to do things in your apps that are just really difficult with more traditional programming techniques. So even just a few years ago, it would have been hard to look at a plant and say, hey, this has X, Y, and Z disease on it, or recognize a bird call from an audio clip. But now we can actually do that with just a few lines of code. So today I'm actually going to go over how you would do that specifically with TensorFlow Lite and Flutter, amongst a few other things. And then actually before we get into that, I did want to talk a little bit about TensorFlow Lite and on-device machine learning. So TensorFlow Lite is actually a tool specifically meant for running machine learning inference, which is the hey, I've got a picture or some other kind of input and I want to get an output from it rather than like the training part of it. But you're able to run that directly from a device instead of having to send that data up somewhere to like a server for processing. So this is going to give us 4 major advantages just from that one single attribute. So we can run inference more quickly since we're cutting out that transit time. This means that if you have a Firebase function that is doing some of the really detailed processing work for you, like image classification, then you can offload a basic version of that inference to your app and then kind of save that time to run the more complex operation for cases that are kind of more complete. So the idea here is, let's say you are doing an app that does produce inspection. You're looking at like wine grapes or table grapes. If you take a picture to have it processed to tell you, hey, this is a Thompson's green seedless table grape up on the server, but you send up a picture that doesn't even have any grapes, you're wasting that time of the processing happening, all the data moving back and forth, getting that response. So if you do a very quick, lightweight version of that to detect just grapes in general on the device, then you're saving all of that effort and time. The next thing to know is that machine learning on a device is going to work when the internet is down or it's unavailable. So if the user is out in a rural area or somewhere with just no signal, like on a subway or what have you, then that is going to be another advantage that you get out of this. And then along with that aspect of never having to have the data leave the device, privacy is going to be preserved, which is particularly useful for situations where you are kind of working with a little bit more sensitive data, like medical imaging or something along those lines. And then offloading ML inference to the end device can also save a ton of money when you're comparing it to doing all of that work on a back end somewhere, especially once you start scaling into the ideas of millions of users. So again, if you're cutting out images that don't meet basic requirements first, then you're able to avoid additional costs from your back end. So to give you an idea of kind of some of the ML things that you can do on a device, I did put together a list of common tasks. So a lot of this is going to fall under the kind of vision category, which is stuff like object detection or face landmarking. But audio classification and natural language processing tasks are also super common. I also threw more in here. Machine learning is kind of a wide array of things that you can do. So this is going to include things like recommendation, understanding speech, upscaling images, generating content, stuff that just doesn't really fit neatly into these three categories, but these are the three big ones. So one of the important things to know about all of this is that TensorFlow Lite is kind of at the heart of how Google does on-device machine learning. Generally, for your own apps, you would take a single TF Lite model, like one for object detection, and then bundle it in with your program. So this is going to let you customize single operations for your purposes. They're, I say fairly lightweight. It can depend, but they're lightweight enough. I think you're going to see roughly around 20 megs for some models, which is not my favorite, but it's not terrible. But then they can be optimized for different device constraints, including memory, computation, power, storage, or really all kinds of other limitations that you might face. So this is actually really useful considering a lot of mobile development or edge or web and all that is about trade-offs. So understanding what you can do to optimize for those trade-offs that are going to make sense for your own apps is going to make a huge difference. Cool, so now that we've done kind of a quick introduction to on-device machine learning and TensorFlow Lite, let's go ahead and get into kind of the more interesting part of this presentation. So I'm going to start with image labeling and classification, since it's kind of the hello world example for machine learning. Along with that, you may have seen this Firebase extension that has its own kind of image labeling tool that uses cloud vision. So this extension is awesome, and while it supports a ton of labels, this model itself is pre-trained. So this means that along with the benefits of doing some on-device early classification, like I had just mentioned before, you might be better off creating your own models specifically for your own use cases, and then also just to kind of trim things down if you don't need thousands of different options. So from what I've seen, most cases that are doing on-device machine learning for image classification need like 20 or less labels. So just to start off, you will need to have a model on the device to perform that inference, since this is entirely on-device ML. If the model's not on the device, it doesn't know what to run that inference against, and the whole thing just breaks. So there's a few ways you can do that, like bundling your TensorFlow Lite model directly into your Android APK or your iOS IPA, or retrieving the model remotely during runtime before it's used, like having it stored up on Firebase storage and then bringing that down. Regardless of how you get your model, though, you will need to initialize TensorFlow Lite. So in this slide, I'm starting off by creating an options object that will handle kind of some of that initial configuration. And then while there's a few different options that you can set, the big one that's really worth mentioning here is hardware delegates. So basically what this does is it looks at the hardware that's on the device, like a GPU or some kind of specialized chip, like the tensor processing unit on Pixels, the TPU, and it offloads the math behind inference to that available chip, basically helping your ML inference run even faster without blocking the device's CPU where it's possible. Once your options are filled in, you can create the interpreter that is going to do really all of the real work for you. So this interpreter is responsible for taking your input data, then returning some output results. So in this case, you can actually see that the input data is going to be 224 pixels by 224 pixels. And then there's 3 layers to it. I'm actually going to get into the theory behind that in a couple slides, just to make this hopefully make a bit more sense where this 224, 224, and 3 is coming in, but it is going to be something you see repeatedly throughout working with ML. So as for the output result, we're just expecting a single array of items representing confidence scores for the 1,001 different individual pre-trained classifications that are available on the given model that I'm using here. One of those is actually background though, so I wouldn't count that. That's kind of the catch-all for anything that it doesn't classify as an actual object. That's kind of for rare cases, and it's not super important, but just good to know. So getting back into the theory part, to make that input make a bit more sense. Let's say that we have a single label classification model, or one that just returns kind of the one most likely label for the entire image. In that case, this image of a cat will likely appear as cat, since it is the most pronounced item in that image. However, if you're using a model that is able to return multiple labels, like our current code sample that we'll have on GitHub and I'll link to in a little bit, then you might see cat, rug, or toy as possible labels all together with a pretty high level of confidence for each of those. Cool, so let's actually take a look at how this is happening at the classification level. So the underlying model that I'm going to cover is using something called a convolutional neural network. The detail's not super important for what we're talking about today, but if you do want to go out and learn more about this, it is kind of a nice keyword to know. So convolutional neural network for image classification, to kind of pick up a lot more of those details when you're reading up on all of this fun stuff. So this tool's main way to approach image classification is to look for patterns within images during training. And then it's going to look for those same patterns in new images. So getting back to this cat image, we can look at it and see different patterns across these different layers for ear shape, eye shape, and nose shape. Now, if we take those patterns and look at brand new images, we should be able to identify those items, or at least most of them, so the model can say that there was a cat in this picture with kind of some level of confidence. So the next thing to know about this classification is that it's happening across multiple layers of an image. So for example, Android may provide an ARGB image, so alpha, red, green, blue. Since the alpha layer doesn't really give us much information, we can just go ahead and drop that. It's just the clear layer, doesn't really matter too much for what we're doing. But then the rest of the colors are looked at to try and perform classification with various patterns being noticeable across those different colors and layers. So if we think back to our code example, this is where that 3 came from in the 224, 224, 3 part of our input matrix. So that's going to represent your red, green, and blue layers. And then finally, images are going to need to go through a few pre-classification steps to scale, shape, or rotate them so they actually match up to the image parameters that the model was trained with. So for example, our model expects images that are 224 pixels by 224 pixels, which again is where that comes from in that input matrix. So you're actually going to need to make sure that your images that you're using for input are going to match up to that size and shape and all that fun stuff that it was trained for. This is called pre-processing. It is one of the generally more important steps when you are working with on-device machine learning, so something else just to be aware of as you get there. Cool, so with the theory part of image classification out of the way, I actually wanted to get back to our code example and how you would make this work in Flutter. So here we have a quick set of example images that use TensorFlow Lite to do image classification using a live camera feed and an image from the gallery. Plus, this app is actually already on GitHub, so if you wanted to just pull that down and run it, it'll already work for you. You can try it out. What's kind of cool about this is the sample that we originally had only worked for galleries and not live camera feeds. So somebody from the community went through and updated it already, put this together so that people have kind of a more practical and interesting example. I'm a big fan of that. So while we created the interpreter already and we defined the output tensor shape, a set of numbers in a giant array just doesn't really tell us much. So to make this more valuable, we can load in a labels file that maps each index to the returned confidence score. And then next you're going to need to get an image prepared for classification. So in this case, I'm just going to grab a single image from the device, then turn it into a list of 8-bit integers using the read as byte sync function off of the Dart.io package. And then once we have a list of bytes, we can create a new image object from the Dart image package. Also, how awesome is the Dart just has all these packages that do so many cool things. Anyway, so then you can use that to resize the image to the 224 by 224 pixel image that we're going to use for our inference. So this next part's a little complex. I did want to cover it here just so you know what to look for when you check out the samples, or if you're kind of looking over the slide decks later. But you are going to need to take that image object and create a matrix that is going to match the 224 by 224 by 3 part of the input tensor, which is going to include separating out the new image into its red, green, and blue layers for each individual pixel. Where this gets tricky is that your image height might not already be in that RGB format, but we do have tools provided that can convert from like a blue, green, red image to an RGB or YUV over to RGB, just to make sure that you are matching exactly what your model is expecting. So once you have that matrix ready to go, you can go put that into one more array to represent your input data. You'll also create an object that represents your output data, but for this case, we're just going to fill that all with zeros, and then once we have the actual information, we'll actually adjust that to match what we expect. And then this next step is where the magic is actually going to happen, as the interpreter that was created with the image classification model accepts an input, and then it returns an output, which really is kind of what the whole goal of this exercise and app is the entire time. So the second line is going to take the output list of confidence scores and remove it from the additional array layer that wraps it so that you can actually start working with those results. And then finally, you just need to do something with those. So in this case, I'm just going to map the confidence scores to the set of labels based off of the array index of each, and then I would display them on the screen. So after all of that, you should be able to take an image, classify it, and see its result label with the prediction confidence scores. One thing to pay attention to here is that you're actually likely going to be getting ints back based off of the model. So for this one, you can see that I have like 90% confidence coming back on the microphone. What's happening here is I'm actually getting a confidence score of like 229, so I have to divide that by 255 to actually get the percentage. Just something to be aware of. Understanding how your data is going in and coming back out is going to make a huge difference in how you are building out your apps and all the like nuances and idiosyncrasies that go along with it. So the next thing actually I think is really cool, which is why I want to talk about it, but it's called super resolution. So while resizing an image down is fairly easy, scaling an image up and then keeping the level of detail still at kind of a good place is just a whole other thing. So there's basically two ways to use super resolution. The first one is going to scale a smaller image up to a larger size while maintaining the level of detail of it. So in this example, you can actually see that we're taking an image that is 50 pixels by 50 pixels and then resizing it up to 200 by 200. And actually in the top left corner here, you can kind of see that we are listing the shapes for the input and the output matrices. So they should look somewhat familiar to you from the last one because those are both images. So you have height, width, and the 3 layers that are going to go with that. And then the second way you can use super resolution is to take an image and really flesh out the details of it without changing its size. So the important thing to remember about this is that earlier we said machine learning makes predictions about the end results. So this technique is actually trying to take a best guess at what it thinks should exist within the image at a higher resolution. So where both the first example of super resolution and this example are really going to shine is when you have something like Firebase storage where you're storing your original 50 by 50 images, you send that down to your app, you display it in your list view. Well, if you want to take that same list view icon, that 50 by 50 image, and then display it on the next page, you can use super resolution to actually scale that up to give you your 200 by 200 or whatever other sizes that you're going to need for your app on that detail screen. So this is going to save you download time, storage on Firebase, and the user's mobile data, which everybody always appreciates, all by basically filling in those gaps as you're working with these images. And then actually there are 4 examples of each image over here. These are actually using the original one on the left side, and then 3 different techniques that you would use for super resolution, filling in the gaps here. Though I'm actually going to talk about the very last one specifically because I think it just has the best amount of detail that goes with it. But this is using something called ESRGAN, or Enhanced Super Resolution Generative Adversarial Networks. So the key part to this is the generative adversarial network part. I'm not going to get too far into the details, but essentially you have a generator that creates an image and then you have a discriminator that's going to try to look at it and say, hey, I think this matches up to what I'm expecting. If it doesn't, it tells the generator, hey, no, I think you can do better, and they kind of just go back and forth competing against each other until you finally get to an image that is able to fool the discriminator as they kind of have this like war games competition against each other. This is actually how a lot of other image generation techniques work. So like those generating apps that you see all over the place now, where you give it a text prompt and then it creates something based off of that. Though ESRGAN is a more specialized version of this technique. So as for the code to do super resolution upscaling, I'm not going to get into too much detail here because a lot of the ideas from the last section in image classification are going to carry over. But as I pointed out with the example slide, the input for this model is a 50 by 50 image, and the output is a new 200 by 200 image. So while these values are fixed by the model that I'm using, you could also retrain your own if you needed like 50 by 50 to 1000 by 1000 and all that kind of fun stuff. Though the engineering for that is a little bit outside of my scope and understanding, so I'm going to just be like, that's an exercise for the reader. So in between the last step and this one, you'll still retrieve the image that you want to work with. Then you can create a new matrix for the image exactly like you did with image labeling. After this, you'll create your output matrix for your new 200 by 200 image, and then run inference. So I'm going to go ahead and just skip that part as well. And then after inference is run, you're going to take your output matrix, which is a list of ints, because us in ML kind of hate ourselves. And then you can start flattening it into a new byte array. And then at that point, you're basically just going to work backwards to create a new Dart object, image object. And then finally, you can just go ahead and convert that into a JPEG and display it, which is what I'm doing, or do whatever else you're going to do in your app. It really just depends on what your situation is going to be. All right, so the last thing I wanted to talk about that is specifically TensorFlow Lite related is text classification. So while this use case is relatively simple, the same concepts around it are going to carry over to most natural language processing tasks that you might run in your apps. So like language detection and some other stuff. For this example, we're actually going to make something that you can take a sentence and then flag the sentiment as either positive or negative. And this is actually really close to what this Firebase extension does, albeit kind of in less detail, but also completely from your device. So where this really shines is that you can do something like prevent toxic messages in your standard super duper Firebase chat app before it even leaves the user's device, and then you have to deal with like security rules and all that kind of fun stuff, giving you that extra layer of scrutiny while saving time and resources on the back end. Out of curiosity, how many of you have made the big like chat app thing for Firebase, that big demo they usually do? Like one person? Two? Oh man. Okay, so there are a couple sessions today. Nohi is definitely doing one that's going to be like make a chat app in 20 minutes. And I think Rosario has a workshop as well at the end of the day. Definitely recommend checking it out. Making the Firebase chat app is kind of the foundational, learn how all of these things work and what they do. And it's just a great way to kind of get embedded into a lot of the cool things that work with Firebase. So, gonna plug that. All right, so to give you an idea of where the text classification example is going, this app specifically lets you enter text into a text field, and then it attempts to classify it as either positive or negative, and then you can just do whatever it is you're gonna do with that app. And then while I'm not gonna get into a ton of detail around how natural language processing works, mainly because it is worthy of its own massive talk and presentations and all this other good stuff, we do have a full video series on the TensorFlow YouTube channel that's going to cover a lot of the background behind this. So for what we are working with, the most important part is that letters or words are matched up to numerical values through a process called tokenization. And then those tokens are going to be assigned a weight towards a classification, such as positive or negative, or really whatever it is that you have trained your model for. So like the other examples, you'll want to create a new input matrix, which in this case is a two-dimensional array of doubles representing the tokens, though we're really only interested in the internal list of those doubles for this example. And then for those of you that are curious, this is actually a simplified text classification example in Python, where you can see how the sentence in the first section is turned into an array of tokens, which is what we're actually going to do in Dart in the next slide, but this is a a lot cleaner. So it's kind of nice to be able to show it this way. Excuse me, sorry. You'll notice that there are 20 different words in the sentence and 20 numbers that are not 0. Though the last 2 numbers that you see in this code snippet are zeros, just to pad out the entire tensor shape of 250 in that dimension. Because basically, if the matrices that you're using for your inputs do not match up to what are expected by the model, then the whole thing is going to kind of end up not working because it is expecting a whole lot of matrices math happening in the background that we just don't really need to worry about, we just need to be prepared for. So getting back to our code example, you can see how this happens in Dart, where we split the sentence into individual words and then fill in a vector with tokens based on those words, plus pad in any remaining spaces and all that good stuff. And what's kind of interesting about this is that the words that you're tokenizing need to already exist within your model via the original training set. Otherwise, the model just isn't going to know what to do with them. So to make life easy, you can actually just go ahead and ignore any words that aren't in the initial dictionary for your classifications, and then just work with what is left. And then going back to the very first text classification slide, you can wrap up by creating your output array, which in this case is just going to provide a value of 1 or 0 for positive or negative. And then you can start calling run with your new friend, the interpreter. So that is what I have today for Flutter and TensorFlow Lite. So if you're interested in this, we have the plugin source up on GitHub, and I'm always looking for people that want to contribute. So adding in new features, making new examples, all that kind of good stuff. I know there's one person, I don't think he was able to make it to this session, who did go through and update a lot of our samples for adding like live camera streams and other stuff to our vision examples. We also have a PR up right now that I need to review today, adding desktop support for Mac, and then there's going to be more of them coming along. So if anyone is interested in contributing, awesome. The one big downside about the way the TensorFlow Lite binaries were written for this, which are directly in the C layer, and then we're using that with this plugin, is that web support just isn't really a thing for the TensorFlow Lite plugin for Flutter, just because TensorFlow JS is using a completely different system for accessing TensorFlow Lite. So to balance that out, I did want to briefly talk about this new thing that we're working on called Media Pipe Task. You might know about this a little bit already from Google I/O and the keynote, and it's currently already available for Python, Android, iOS, web, and the Raspberry Pi. Raspberry Pi is just another iteration though on Python, so that's nothing too fancy. But recently, Craig from the Flutter team and I have been working on getting a Dart version together, specifically to make machine learning basically a bit easier for our Flutter devs. So back at the start of this talk, I showed you all this slide where you saw that you can take an input, which we now know is a matrix of values, and you get an output, which is another matrix of values. And I'm sure a lot of you have had the same thought that I have had while I've been working with this and writing this talk, and now that I'm giving this talk. This is terrible. Nobody wants to have to go through and deal with all these matrices and trying to get all the data formatted in this very fancy, special way to make this work. So we know, and we are working on it. So as you all saw, there is a lot more to ML than just running inference. But you also need to do things like flow control so that your app isn't sending data faster than it can be processed. End-to-end pipeline acceleration for improving performance on your models, which is like what we saw with the hardware delegates and actually being able to use the GPU or the TPU. Or just pre-processing your images so they work specifically with what your model is expecting. This altogether is called an ML pipeline, and they streamline the process from your initial raw inputs all the way to your output results. So to give you a better idea of what we're working towards, I just wanted to include a quick snippet from an Android app that is hand gesture recognition, mainly because it's very similar to what our other platforms are doing, like how the code is written and what it looks like. And it is very, very similar to what it's going to look like on Flutter once this is ready and launchable, hopefully in the next couple months. We are working right now. I know we've got a general prototype working for text, and then we're getting the other stuff put together. Anyway, so for step 1, we have a standardized options object that will accept your model, though in this case it's actually a bundle of multiple models put together that are going to run in series. And then you can give it other additional options like a confidence threshold or how confident your model needs to be in the result before it even tells you about it, as well as the max number of results that you want to get back. So if you want to only have one item that has been classified as thumbs up, or if you want to know, hey, it could be thumbs up, thumbs down, hand open, whatever, you can get back all of those with their confidence scores. After that, you can create the recognizer object that is going to do really a lot of the pre-processing, like flow control, along with that inference. And then from there, it actually gets a lot easier. So you can just take a bitmap, turn it into a new media pipe image object that will handle all of the layers and other concepts behind shaping images. And then just call recognize from that recognizer object at the top to get an already formatted set of results that you can work with without really any additional processing. So in the case of gesture recognition, you can get back a list of landmarks on a hand, additional information about each landmark, and the likelihood that the given gesture is one that it was trained for. And what's cool about this too is you're actually getting this back as like a regular data object rather than getting back a matrix and having to try to figure out what each of those values in the matrix like is even represented by. Just makes things a lot easier to be able to work with in an actual object-oriented language. So do we have all landmarks on there too? Yeah, so there's the landmarks and there's ruled landmarks. There's also all kinds of other cool things you can do with that. With ruled landmarks, you're able to essentially try to take the information about those landmarks on the hand, and it tries to correlate it to real-world space too, so it'll essentially make it relevant to meters, distance from the camera, and all kinds of other stuff. So there's some cool stuff you can do with this with augmented reality based off of that. So here you can see that I'm actually using this to classify thumbs up, thumbs down, closed fist, and open palm with a pre-trained model bundle. Though we actually also provide a tool for retraining that bundle with your own custom gestures for things like a game of rock, paper, scissors, or anything else that you want to have in there. And then the other cool thing about this is that gesture recognition is working through 4 separate steps, and each of these steps are made up of their own models that are chained together in their own pipeline, rather than what you would normally have to do with TensorFlow Lite, where you take your input, run inference, take that output, and then take that output and then kind of manipulate it to fit into the next model. You just keep chaining these together in a very kind of cumbersome, awful process. We just try to streamline that as much as we can. So the first model is going to attempt to detect the presence and location of a hand before even moving on to the next phase. And again, if it can't find a hand like at all within that image, it's not even going to bother running the next steps because it's just bound to fail. So it's a little bit of a way to optimize that. The next phase is going to attempt to locate useful landmarks on the hand, such as your knuckles, your fingertips, and the central base of the palm. The third is going to convert those landmarks into a vector embedding, which is just a way of representing where those landmarks are and kind of comparing it to what it's already aware of and knows. And then the last one is going to take those vector embeddings and try to figure out what gestures might be made that it's been trained for out of the 7 that are out there with this particular model that I'm using. And then there's the Face Landmark API, which will, again, also be out there in Flutter as soon as we have this all done. As you might guess, this task helps you identify specific landmarks on a face. The default model for this is going to estimate 478 3D face landmarks in real time, and it's only using a single camera rather than multiple, even though it's able to kind of take a best guess at location and depth within the real world compared to the images that are coming in. It's also kind of cool is that it's able to track those points. You can kind of see as I'm moving my face, it's able to say, hey, your nose is moved this way, or you can kind of see the chin points kind of move off to the other side as I tilt my head. And then on top of those landmarks, this also is able to try to determine different attributes to the face, such as eyebrows raised, smiling, eyes closed. And there's something like, what is it, 50-something? Yeah. Blend shapes for each faces that you would be able to use if you want to be able to use those gestures to do whatever it is with your apps. And then the last thing you get from this task is a set of transform matrices that you can use for things like applying augmented reality to your apps, so skins over the camera face. So here you can actually see that I kind of was able to make a raccoon face that I was able to apply using media pipe onto this graphic. Actually, augmented reality is really complex too, so if anybody does want to play around with this, do tutorials, talks, all that kind of fun stuff, I think it would be really useful for the community. So just going to throw it out there, but it is really fun and awesome stuff. So, and then since that earlier gesture recognition example only works with static gestures, I wanted to mention that you can actually expand your apps to record multiple types of landmarks together over a period of time in a sequence to pass that data to a new TensorFlow Lite model rather than a media pipe portion of this that can handle things like sign language to do even more cool things by combining both the ML tech that we've talked about today, so TensorFlow Lite and media pipe. So in this example, you can actually see that I'm able to detect myself doing American Sign Language for shower, donkey, and frog. But because of the accuracy of it, you can also detect things that are similar, like cow instead of donkey, and then is it like frog instead of pig? So even though they're similar, it's able to detect the differences in those based off of the accuracy of the landmarks. Cool, and then to wrap up, I just wanted to kind of touch on generative ML, since it's one of the more interesting things we have running completely on device. So while we are working on a few different tasks, the first one that we're releasing, we actually just released it like last week, is style transfer, and specifically face stylization. We actually have an example for style transfer specifically with TensorFlow Lite as well, and that's all on the GitHub repo for the Flutter plugin as well. But basically, this is going to let you train a model that uses a single reference image, and then use that model to apply styles to a new face to create a stylized image. So here you can actually see that I have this Gibson 1910 ink picture, and I'm able to extract the styles from that and apply it to a new person to kind of get a version of them kind of drawn in that style. This actually be kind of something cool too if you're going to use it with Firebase to make avatars for your user accounts and that kind of fun stuff. And then the second type of generative ML is actually image generation, which you might use for users to create content that you then store in Firebase storage or what have you. So rather than the GAN technique, which we saw for both face stylization on the last slide as well as super resolution, we're using something called diffusion. So essentially this works by taking some text, figuring out what the keywords are in that text to try and create new content based off of the things that it thinks are related. And then it creates these staticky general images that it then tries to de-noise as it gets closer and closer to what it thinks should be the final result. What's actually really cool about this too is that here we're able to create a new image within some seconds. I think it's roughly, if you're not showing the intermediate results, you're looking at like 20 seconds. If you are showing the intermediate results, because that does take a little bit more processing out of it, it takes like a minute. But it's faster as you do different things. There's a lot of other optimizations you can do with this. And what's actually kind of cool about this is this is actually the plugin for Android that we announced a couple months ago. And then we actually just got it on GitHub on Friday because I just finished the sample. And then we'll have like more documentation and stuff coming out this week. So I got the green flag to actually talk about it, so I'm pretty excited about that. But there are a few different ways that you're able to use this. So the first one that you have on the left is just basically text in, generative image out. The second one is one that's using something called plugins. So you can use like a face, and it'll find face landmarks on that and use that as the foundation for the image, which is why the like statue is kind of facing the same direction that I am. We're also able to do edge detection and depth mapping to be able to use those as like kind of foundations for the model. And then the last one is using something called LoRa weights, which are essentially a way that you can train additional parts to a model to introduce biases towards specific like objects and concepts and all that kind of fun stuff. So for this one, we actually took 8 images of this particular kind of teapot, put that into the model that we're using on the device. And then anytime we say, hey, generate a teapot, it's going to be this particular kind of teapot that gets generated. So if you had a product that you wanted to put into your images or whatever, you'd be able to do it this way. Anyway, if you're interested, I can talk about this for quite a while more. Come find me. I will go over it. We will have the samples and all that stuff very publicly here very soon. Hopefully this week. I'm actually going to work on some of this stuff tonight. So with that, I have a few links up here that you can use to kind of keep up with the latest of the MediaPipe news, including announcements as we get closer to releasing the official MediaPipe plugin for Flutter, and example apps for the platforms that we already support. And again, this is the GitHub link for the TensorFlow Flutter plugin, as well as the pub.dev site where you'd actually be able to go and grab that plugin to install it on your device. Again, my name is Paul. My email is here if you want to bother me that way. If you would rather like actually write out your thoughts, that's totally cool too. You can find all that information there. And then the last slide I have here is just the actual slide deck with all of this information, so you can find it there as well. So cool. I think we are kind of iffy on time for questions, but I will be around. Come find me. I will love to talk to everybody. Thank you.